Welcome, Calculus BC. This is lesson 5.4, log functions and log derivatives. Let's go. So what is a log function? Well, a log function looks like this. It's kind of going up like this, and it'll go up a little bit and go out. So you have a few properties right here. The graph is going to be approaching this asymptote. So you actually have an asymptote, and this, let's see, the function y equals ln of x, or y equals log of x. One of these functions. The asymptote's going to happen at x equals 0, so right here on the y-axis. Your domain of this function right here, which is all your x values, will be from 0 to infinity. So everything positive, but not including 0. Your range is going to be all real numbers. So positive infinity, negative infinity, because they're always going up a little bit and going out. So that's what a log function looks like. It's kind of like the inverse of an exponential function, if you remember from last chapter. And that'd be a function that kind of does this, going up. So kind of like the mirror of that. Changing exponential to log, a review of Algebra 2 skills. So exponential form might look x equals e to the y, and that can convert y to the e to the x. Y equals ln of x. Think of it this way as like log base e of x equals y. That's how I kind of thought of it. Ln of x is the same thing as log base e. And, you know, same way you can convert back and forth. It's one of those things to memorize. So if I want to change these, 3 to the 4th power equals 81, I'm going to go log base 3 of 81 equals 4. So log base 3 of 81 equals 4. All right, same here. Now if I say just log, I mean log base 10. So I'm going to convert this log function to an exponential function. The way I think of this is a to the y power equals x. Like you go back and forth. And I always think like going from the bottom up. So like a is the lowest, to the left, to the right, whatever. So this will be 10 to the negative 1 power equals 0.1, which is true because 10 to the negative 1 is 1 over 10. So there you go. A few other things. So if e to the 0 equals 1, ln of 1 is going to equal, that's like log base e, that's going to equal 0. So actually log of 1 is always going to equal 0. That's one of those things to know. Right here, e to the 1 equals e. The ln of e is going to equal 1. Another thing to know. Log base e to the n is equivalent to e to the ln of n, which both equal n. Kind of like the log and the exponent cancel each other out in a way. You can think of it that way. A few of the properties of logs, back to your Algebra 2 days. Product, quotient, and power rules. So if you're multiplying them as a product, you can split it up with addition. If you're dividing them as a quotient, you can split it up into the top minus the bottom. And then if you have a power, you can actually take that n and it can go outside as a coefficient, and those are equivalent. So maybe if I wanted to like take a problem like this and expand it, this would expand to natural log of 5 minus log of 8. This one, so this cube root is the same thing as x squared plus 1 to the 1/3 power. So I can rewrite that as 1/3 natural log of x squared plus 1. No, you can't just, since they're connected by pluses minuses, I can't just take out that squared. I can't break this up either. That's the best I can do. If it's plus in here, it doesn't work this way at all. These ones I want to condense. So I'm going to condense this to a power. So this is the same thing as natural log of x to the negative 3rd power plus natural log of y to the 5th power. Since it's plus, they're actually multiplying. I can rewrite that as natural log of x to the negative 3rd times y to the 5th. So there's a way to combine. This one here, notice this one's being combined, subtracted here. I'm going to rewrite this as minus ln of y cubed. And this is going to be ln of x to the 1/2 power. And this thing stays the same. Since these two are being added, I'm going to put those on top of the fraction. So it'll be ln of x to the 1/2 power times x plus 1, and then the y cube's actually, since being subtracted, it's going to be in the bottom y cubed. So that's how the properties of the logs work. Change of base formula, this might come up too. So the idea is that you have like a log base a of x, like a weird base, and you can change it to a different base, and this can be any base. So it'll be like the log of x over the log of a. And this could be any base. So this is useful when you want to find weird logs with a calculator. So like if we look at our calculator over here, let's say if I wanted to do the problem log base 3 of, I don't know, 10. I don't have a log base 3 on my calculator. In fact, if you go to your 83 or 89, you usually only have two buttons. You have like a log, which is log base 10, and you have natural log, which is log base E. So on a TI-89, let's say if I want to do log base 3 of 10, what I'm going to do is I'm just going to say natural log of 10 divided by natural log of 3. And this is giving me my answer. So just like that. So that's how I'd solve those kind of things. So yeah, you want to find the weird logs. So that's how you do those things, and I could have done any example. But there you go. All right, derivatives. So this formula, derivative of natural log, is 1 over x. Better memorize that. We also have derivative of any log-based x would be 1 over x times, put the natural log of a on the bottom. This is similar to those other formulas you've seen. So 1 over x, but you also put this ln of a on the bottom. This doesn't happen very often, but here it is, just in case it does. This is the one you really need to memorize. So let's do 11 right here. Remember, you're still doing chain rule. So if I want to differentiate that, the ln of 5x is going to be 1 over 5x. It's just basically put the inside on the bottom, times the derivative of the inside, which would be 5, which actually reduces to 1 over x when the 5's cancel. A neat thing on this problem, what if I would use the product rule? I could have broken that up into y equals ln of 5 plus ln of x. And then if I derive from this point, ln of 5 is a constant, that's just 0. And ln of x is 1 over x, so actually it's also 1 over x. So there's two different ways I could have approached that problem, and that's kind of nice in log problems. Sometimes it's easier to break those up before you log them. Okay, let's keep going. So sometimes you have weird things like, there's a lot of words going on here, but y equals x to the x power. Like your x is your base and your exponent, or in any of these weird cases. So when you have the x as a base and the exponent, you got to do something called logarithmic differentiation. Does this happen a lot in AP classes? I don't know. But so the key part of doing this, and I got the procedures here, is we're going to have to do a natural log of both sides first. You're going to have to ln both sides. And then we got to do like implicit differentiation to get your y prime and blah, blah, blah. So let's take a case of, let's say I got an example in here. Oh, that's way too hard. I'm going to do the example y equals x to the x power. And I want to find y prime, okay, or dy dx. So what I'm going to do is I'm going to ln both sides first. When you ln both sides, this is just ln of y. And what's cool, what happens with this one, remember your exponent rule, power rule, I can bring that x to the outside. So I can say ln of y equals x times ln of x. And now we are going to differentiate both sides with respect to x. So derivative of y is going to be 1 over y times y prime. Remember when you derive a y. And then this I'm going to have to break up with product rule. So this is going to be 1, derivative of x, times ln of x, plus x times derivative of ln of x is 1 over x. And that can clean up to be ln of x plus 1, the x's cancel out, equals 1 over y prime. Cool. So I want to solve for y prime. I got to, on both sides, I want to multiply by y. Remember, you're multiplying the whole thing by y, and these cancel. So my y prime equals ln of x plus 1 times y. Now, if I want to just express my answer in terms of x, what I'm going to do instead is, back in the original case, we were told y equals x to the x. So I can plug that in for my y and say y prime now equals ln of x plus 1 times x to the x power. Looks gross, but just did the work. All right, I think that's it. Yep, we're done.